But that's only one aspect of TRON project, and it's actually not TRON. It's not just an embedded platform, but it's actually has been an IoT project continued for more than 30 years. So that's why I'm here to tell you about TRON. So TRON project has been started by Professor Sakamura in 1984 and continued to be the IoT project for more than 30 years since then. As far as I know, no other IoT project has continued to for so long. The Springer book given here shows that it is an IoT project, not just an embedded platform project. So the objective of the TRON project is to realize highly functional distributed system, HFDS, using the term described in the previous book. Its idea is to let network interconnected intelligent objects cooperate with each other to realize optimal environment, which cannot be realized by single devices alone. The term IoT mainly focuses on connecting through the network, but HFDS can be considered an ultimate goal of the IoT that can be realized through the technologies of the IoT. And in 21st century, TRON project was divided into two subcategories so that realization of HFDS are accelerated. And the first one on the left is the T-kernel 2.0 T2 project, which aims to realize HFDS in a bottom-up approach. And its focus is on designing software for IoT-enabled embedded devices. And the other one on the right is the IoT aggregator project called U2, which aims to realize HFDS in top-down manner, the opposite against T2. And its focus is on realizing practical interoperability required in the IoT. So it needs a framework outside the device. And here's the total architecture made by the TRON project. As given in this figure, device-side architecture is covered by T2, while cloud-side architecture covers the interoperability issues in the Internet of Things. Apparently, doing either of these is insufficient for successful deployment of IT in real life, and that's why we're doing it from both sides. And we're supported by many industries and academia from all over the world, including the Imagination Technologies and other companies like Casamedia and many others. As we have influential embedded system platform, many companies involved in embedded system join a project to realize the IoT based on TRON architecture. But recently, we're cooperating with many other industries like service industries for creating the application business for the IoT. Other companies include health makers like Daiwa Building, and etc. So this is the brief overview of the TRON project. So from here on, I would like to explain a little more detail about the developing consumer electronics with TRON and connecting the IoT, connecting them to the IoT with T2, and then orchestrating the IoT devices with TRON. So the developing consumer electronics with T-kernel 2.0. So as you may already know, TRON operating system is one of the most commonly used operating systems in the world. According to a survey, TRON operating system share is about 60% and has had the topmost share for more than 20 consecutive years since 1999. And the latest TRON operating system is called T-kernel 2.0, which is a scalable, highly efficient real-time operating system for embedded system in the IoT age. For example, in IEEE, this is a figure taken from the IEEE Micro, and it has been reported that Micro T-kernel outperforms the other real-time operating system with respect to the task switch time and task activation time for interrupt, as you can see in the figure. And some of you may ask, why not embed Linux? Yes, actually, Linux is a very good operating system, and it's now often accepted in many of the embedded use cases. And although it is a very good operating system, it is not always adequate because of its complexity. So let's compare the boot process of Linux with TRON 2.0. In usual Linux, in order for the system to boot, you need to do the whole of the left things. So this is a lot of things must be done. And this makes system to boot, for example, in about 10 seconds or more, or even 1 minute. Such boot time is often accepted in information devices like PCs or smartphones, but may not be in embedded systems. For example, if you have a digital camera, if the digital camera needs 10 seconds to boot, you'll be angry. So for embedded systems, the requirement is very different. And so the boot process of Linux and other general purpose operating system can be a problem. And one example showing the difference, the actual difference, can be the boot time of the IoT routers. One made by some American company, and it's made of Linux, and the other is actually our product. Based on the TRON 2.0. Although our product is much more functional than the other, our product outperformed in boot time. While Linux-based ones took 2 minutes to boot, our product boots in less than 0.3 seconds. Hence, we can confirm here that TRON is a good platform with respect to performance. And as Ishikawa-san has already discussed, in order to extend the TRON 2.0 applicability from small scale to large scale embedded systems, we provide several versions of TRON family. TRON 2.0, which is the standard version, which is extensible standard configuration of TRON, and T2EX, which is the TRON 2.0 extension, which adds efficient memory protection, file system, and network functions to TRON. And AMP and SMP TRON is for multi-core and multi-core processor systems. And the last one, the micro TRON 2.0, is for small-scale embedded devices with resource constraints. So with, for example, with limited ROM and RAM, 16-bit CPU, etc. And this one is, when considered that this variation, micro TRON is a key element for the IoT, because sensor nodes and IoT nodes are very resource constrained. So micro TRON is the smallest version in our TRON 2.0 family, and it is considered most suitable for resource constrained IoT nodes, as it can work with 8 kilobytes of ROM and 4 kilobytes of RAM. And we have also taken another approach to improve traditional TRON operating system, and it's significantly improved micro TRON performance. For example, we have added service profiles for allowing optimized implementations of micro TRON 2.0 and added use of constant displayers. And we have succeeded in reducing 8 kilobytes of ROM and 1 kilobyte of RAM in standard configurations through these improvements. We can proudly say that it is a perfect choice for the IoT nodes. And micro TRON 2.0 is basically free of charge, and you can download it from the TRON page, TRON web page, as given here, www.tron.org. However, please note that in reality, only source code is not enough, and you will need some extra tools that actually developing software for electronic devices. For instance, you need a development boards unless you want to make specific boards by yourself, and you also need a debugger and serial writers in order to write programs in a flash ROM, and you also need editors, assemblers, and compilers. And in some cases, simulators would be needed. But don't worry, and all-in-one SDK packages are available for multiple vendors in multiple forms for your ease in development. So, and if you still want to save some money for development, free tools are also available, like GNU ARM embedded toolchain, and I'm the one that is using these tools because we don't have much money. And if you use an SDK, development is just as simple as native Windows and Mac OS application development. So for example, you first connect the development board to your debugger, and then open the project file, and then press build button, and then start debug session through the D button. So this is the whole process. So it's, the programming embedded system can be done equally simpler as the Windows and Mac OS development. The programming model of TRON family operating system is based on multi-thread systems, which is convenient for doing multiple tasks with a single computer. For example, in case of a refrigerator, you need to do this different tasks at the same time. For example, motors need to be turned and sensors need to be handled simultaneously. So multi-thread model is a good choice. However, please note that the scheduling is based on fixed priority, unlike round-robin or CFS scheduling taken in general-purpose operating systems, like Windows and Mac operating system. Fixed priority means that each process is given a priority value, and preferred ones are always executed first. For example, if Excel is given higher priority than PowerPoint, the execution of PowerPoint software will always suspended until Excel stops running. But Excel can interrupt PowerPoint execution and run while PowerPoint is running. This sounds very ridiculous because it's a PC. PC users prefer these software to run equally simultaneously, thus threads are run equally on these platforms. On the other hand, real-time operating systems are designed for embedded systems requiring real-time behavior, not fairness among processes. Embedded devices have timing constraints. For instance, in case of a car, brake pedal response should be done in a fixed small amount of time. It should not be interfered by car audio, for example. Such brakes and motors have deadlines that defines the response time limit that should be scheduled based on the priorities. So that's the big difference among the general purpose operating system and the real-time operating system. So using T-kernel 2.0, running threads is quite simple. Creating tasks can be done with TK create task function, and starting it can be done with a TK start task function, as can be listed in the figure. And I will not go into the details, but the T-kernel 2.0 is equipped with rich inter-task communication functions is listed here. And because efficiency of the task handling is very important in real-time operating system, T-kernel 2.0 is designed as a feature-rich operating system with respect to inter-task communications. And of course, you can do the whole thing with only a semaphore, but by using these functions properly, the embedded programming is made more productive and made more efficient. And please note that because T-kernel 2.0 is an efficient real-time operating system, they're used in many of the mission-critical and time-critical systems. One example is high-end digital cameras, which need to boot fast, sense, focus, and actuate fast for the focus to switch fast, for example. And another example would be the space industries. Some satellites and Japanese spaceships load TRON operating system for reliability. And the detailed specifications and source codes are all available at the TRON forum webpage. So if you're interested, please visit www.tron.org. So to summarize this section, T-kernel 2.0 is an operating system that scales from small systems to large systems and has academia and industry's proven performance and efficiency, and is used worldwide as one of the de facto standards, and is highly usable, feature-rich operating system designed for the age of IoT. So next, I would like to move on to connecting to the IoT with T-kernel 2.0. So apparently, for realizing the IoT, the connectivity in IoT is very important because without it, devices are excluded from the IoT. And many TCP/IP protocol stacks for both LAN and wired LANs are all available for TRON 2.0, ranging from free ones to commercial ones. And basically, you can use them to build up IoT devices, but it is not always the optimal solution. So let's think about the unplugged devices. If you want to make your existing house smart using the IoT technology, unplugged device support would become necessary. If you want to make the door of your house smart, you basically would need to ask for an electronic engineer to make a hole in the wall, and then pull the electricity lines to provide the power for the door, and open the walls, and attach the circuits inside the door. So it is very difficult. However, if the devices need no electricity lines, adding it to your house is very simple. You can, some products, this is an actual product from Sony that can be attached to existing door. So it's very simple. For making such unplugged device systems, what is the problem is the power consumption. To use standard Wi-Fi technology for this purpose is apparently not good because it consumes a lot of energy. Batteries would not last for a few days considering the battery lifetime of the smartphones and mobile routers. I don't think your smartphone will last for 1 year, right? So in order to overcome this problem, many alternative technologies have been developed, like IEEE 802.15.5 series of protocols, Bluetooth Low Energy, and passive Wi-Fi, and so on. Indeed, Bluetooth LE technology is used in unplugged smart locks system Curio, as given in the previous slide, and it lasts about 300 days with two lithium batteries. So there are many other alternatives for unplugged devices, but please recall again that connectivity is important.